Lokesh and Vimala. My screen is visible to you.
Yes, sir.
Is it okay? My screen is visible to you. Screen sharing. Yeah, okay. Thank you. Now this acetone is taken as the symmetrical carbonyl compound for the explaining the mechanism of nourish one reaction. Now, as previously explained, this reaction proceeds through the formation of N2,5 triplet state intermediate. In this case of acetone, we are using triplet sensitizer, or sometimes we can also conduct the reaction on direct irradiation with light. Then it produces corresponding excited states. That is N2,5 singlet state. First one is. Then if you are not using here triplet energy photosensitizer here, the excited state is stopped here after formation of N2,5 excited state. Suppose if you are using the photosensitizer like acetophenone, benzophenone, or naphthalene, like that, this singlet state will be converting into corresponding triplet state energy. But here I am conducting the reaction with the N2,5 singlet state. Now this will be undergoing homolytic cleavage of alpha bond. You know that alpha bond, this is the carbonyl carbon, this is the alpha carbon. The carbonyl carbon and the bond between the carbonyl carbon and alpha carbon, this is known as alpha bond. This alpha bond is undergoing the homolytic cleavage that leads to the formation of two radicals. That is this radical and methyl radical. Now, after formation of these two radicals, it may undergoes three kinds of path. It chooses the three kinds of pathways. The first one, here another alpha methyl group is there, from which it leaves the hydrogen radical. Then it leads to formation of a ketene intermediate. This is the ketene intermediate. Okay, this hydrogen radical removes from at the alpha carbon. That means that in the three hydrogens, one hydrogen is eliminated as a hydrogen radical. That leads to formation of ketene. And the second mode of action, that is the second pathway, dimerization. Here the dimerization may takes place by the methyl radical or carbonyl radical. Therefore, two kinds of products are generated. Then if you take the first dimerization between the carbonyl radicals, then it leads to the formation of diacetone is generated. That is the diketone is generated. This is the dimerization. And another dimerization between the two methyl radicals. Dimerization that leads to formation of ethane is the product. Now this is the mechanism takes place when the symmetrical carbonyl is participating in the Norris type 1 reaction. Now coming to is the unsymmetrical ketone. If you take example for the symmetrical ketone, another example is we can take the cyclohexanone. The cyclohexanone is also example for the symmetrical ketone. When this is also on direct irradiation, it is also leads to formation of two same biradical intermediate, because it is a cyclic product. At the alpha bond cleavage, it leads to formation of 1,6 biradical intermediate. After formation of this 1,6 biradical intermediate, leads to the formation of three kinds of products. One is aldehyde. This is the aldehyde, acyclic aldehyde actually. A cyclic ketone broke down in the Norris 1 cleavage that leads to formation of one of the product is aldehyde. And a ketene is also generated, is similar to the acetone. It is also similar to the acetone, but the number of carbons are increased. CH3. A cyclic product is generated, that is the number of carbons on the cyclic system will be reduced to 6-member to 5-member. A cyclopentanone derivative is generated. How it is generated? Now, first it is, if we are using sensitizer here, what is the sensitizer we are using? Suppose the benzophenone is used. Benzophenone. The benzophenone, because allylic system is always exist in the form of allylic or saturated carbonyl compounds and irradiated with light. They are stopped at the formation of a singlet N25 star transition state or excited state. This N25 star singlet excited state will not converting into triplet state in the absence of sensitizer, because that energy gap between the T1 and S1 is very much large. Due to that reason, whenever we are using the sensitizer, that triplet energy transfer will be takes place. Here, the allylic ketone will not absorb the radiation. Only sensitizer like benzophenone or naphthalene like molecules absorb the light energy. Then they gets the excited. First, it forms the N25 star singlet state. Simultaneously, the energy gap between the singlet state and triplet state, that is S1 and T1, is very low. Then the energy is transferred from the singlet state of benzophenone to cyclohexanone triplet state, T1 state. Then it leads to the formation of first it is under radiation. It leads to the formation of N25 star singlet energy transition state. Then it is undergoing intersystem crossing, ISC. Then it leads to the formation of N25 star. When it is happened, we are using the sensitizer. Now this is the triplet state. This triplet state. What is the triplet state? This is the triplet state. Triplet excited N25 star state. N25 star state. Now it is undergoing the alpha cleavage. This carbon and carbonyl carbon and alpha carbon bond will be undergoing the homolytic cleavage that leads to formation of 1,6 biradical intermediate. This is 1,6 biradical intermediate. 1, 2, 3, 4, 5, and 6. This is known as 1,6 biradical intermediate. This 1,6 biradical intermediate chooses the 3 paths. The first one is formation of aldehydes. How it aldehyde is generated? Then this is the, when you comparing the here, the olefinic bond is also there. Then 1, 2, 3, 4, 5. 1, 5, 1, 5, 1, 5, unsaturated, unsaturated aldehyde, or 5E hexanaldehyde, hexanal or hexanaldehyde, right? That is the product. How it is generated? Like here, this is the already generated radical. Here the hydrogen is there. When the same energy state, this bond will be broken down. CH bond will be broken down. This hydrogen, it is undergoing the homolytic cleavage. After the homolytic cleavage, this hydrogen radical is generated. This hydrogen radical is captured by this carbonyl or carbonyl carbon radical. Then it leads to formation of aldehyde. Then here at the adjacent position, 2 radicals are there. These 2 radicals combined together, they generate the double bond. How it is? This is the intermediate after the capturing of hydrogen radical by the carbonyl carbon radical. Now there is one radical and second radical. Both will homolytically combine together. That leads to the formation of double bond here. Now this leads to the aldehyde product. This is one pathway. And the second pathway, here at the second position, CH bond is there. It is undergoing homolytic cleavage. This is the first pathway. When we consider, this is the first pathway. The second pathway, here the CH bond is undergoing the homolytic cleavage. Hydrogen radical is eliminated. Then once the hydrogen radical is eliminated, there is a radical generation at the second carbon. Then the second carbon and carbonyl carbon radical both together homolytically combine together. then generates the ketene intermediate. Hydrogen radical is eliminated. Then it leads to the generation of this ketene intermediate. This is the second pathway. And third pathway. In this third pathway, if you choose this, here the hydrogen radical is generated. This hydrogen radical is taken by this previously generated CH2 radical. Now this will be converting into CH3 group. There is a remaining newly generated radical position is happening here. Then it leads to the formation of 1,5 biradical intermediate is generated. This is 1,5 biradical intermediate. At the fifth position, new radical position is generated. Now these two homoletically combine together. Then it leads to the formation of a 5-membered ring. 1, 2, 3, 4, and 5. That means one first carbon and fifth carbon homoletically combined together. That generates the 5-membered ring. Therefore, the cyclopentanone 2. Yes, alpha methyl cyclopentanone is generated. Alpha methyl cyclopentanone is generated. Now, what are the products? 3 products are generated. One is the aldehyde, another one is the ketene intermediate, and third one is alpha methyl cyclopentanone. Now, other examples, if you take unsymmetrical ketones, if you take the unsymmetrical, the mechanism is same. If you are unsymmetrical ketone or symmetrical ketone, mechanism is same, but the product generation is different. If you take the unsymmetrical carbonyl compounds, now take same cyclohexanone, but it is the substituted one. Alpha dimethyl cyclohexanone or 2,2-dimethyl cyclohexanone. 2,2-dimethyl cyclohexanone. Right. This is unsymmetrical carbonyl compound. This unsymmetrical carbonyl compound, which is in the solution, the medium is, that means solvent is added, the solution is generated, is an irradiation. That leads to the formation of 4 products. 4 different kinds of products are generated because the availability of at the alpha position substitutions are increases. Therefore, the formation of products are also increases. The first product is an aldehyde. As similarly previously explained. One is the aldehyde product. That is 6,6,6-dimethyl heptanaldehyde is generated. This is the 1, 2, 3, 4, 5, 6. 6-methyl 5-ene heptanaldehyde is the product. Right. The second pathway, and the second product is a proton exchange. Proton exchange means hydrogen radical exchange on removal. That leads to the double bond position will be changed. Double bond position is changed. That leads to the formation of CH2. This one is the second product. And the third product, ketene intermediate generation. These 3 products are very much similar to the previous reaction. CH3. Now double bond, C double bond. This is the ketene intermediate. Hydrogen is there. Hydrogen. This is the third product, and 1,5 biradical rearrangement. This 6-position radical, actually there is a after cleavage of this homolytic cleavage of this cyclohexanone 6 radical 1,6 biradical intermediate generated. This radical is rearranged to 1,5 biradical intermediate. That leads to the formation of cyclization. Due to the cyclization, that leads to the formation of a cyclopentanone intermediate is generated. Cyclopentanone intermediate is generated. Yes, but here, whenever it is right, just a minute. Here, this is due to the decarbonization. decarbonylation that leads to the formation of cyclopentanone derivative. How it is generated, I will explain this just this pathway only, because the previous three are already explained, are already known how they are generated. Now, okay, you take this is the starting material, that is 2,2-dimethyl cyclohexanone. The first Norris cleavage, it leads to the formation of 1,6 biradical intermediate CH3. Here the radical is generated. At the same time, here the carbonyl carbon is also getting the radical nature. And the second homolytic cleavage of the Norris type 1 reaction is happened. Then it leads to the formation of carbonyl is eliminated. 1,5 biradical intermediate is generated. This 1,5 biradical, here one radical and the second radical. These two homolytically combined together, that leads to the formation of a bond between them, between the two radicals, that leads to the formation of 1,1-dimethyl cyclopentane. 1,1-dimethyl cyclopentane is generated. Similarly, we can see the reaction in the vapor state. It is a solution phase reaction. It leads to the formation of four different products. But the product ratios are also we can limit or prohibit the formation of other products also, because based on the usage of wavelength of light in the reaction. If you are using a specific wavelength of light in the reaction, only one kind of product may be possible, that is the stereospecificity. That stereospecificity depends on the wavelength of light used in the reaction, right? Now, and also solution reaction medium also affecting. Here the cyclopentanone is taken in the reaction. The cyclopentanone is irradiated with the light in the vapor phase. This reaction is conducted in the vapor phase. That leads to formation of aldehyde, that is alpha, beta, gamma. Alpha, gamma, delta unsaturated aldehydes are generated. At the same time, cyclobutane is generated, and sometimes it also leads to the formation of ethylene. Other three different products are generated. This reaction takes place in the vapor medium. Several other reactions are there. You can read your book. You can get more examples. Okay, I'm concluding the Norris 1 reaction here, and then take somewhat extension reaction to the Norris 1 reaction is Photophase reaction. Photophase reaction is very much important for the examination also. Photophase rearrangement reaction. How many of you know freeze rearrangement reaction? Not the photophase rearrangement. Actually, in a conventional freeze rearrangement reaction is there. Anybody knows what is the freeze rearrangement? Please answer, anyone. The 11 members are there. Anyone, you can answer. What is the conventional freeze rearrangement? What's happening? What are the products? Venkatesh, Jayashree can reply. Not remembered? Yes, okay, I will. This is the ester, aromatic esters. It is a very much specific to the aromatic esters. Suppose this is the ester, phenyl acetate. This is the phenyl acetate. This phenyl acetate is on heating with aluminum chloride, AlCl3. It is this temperature dependent reaction. If you take the temperature at 120 or 160, two conditions, then it leads to the formation of, actually it is the solid phase reaction. Just mix the starting metal with the AlCl3, just heat it, no other solvent is required. Then it leads to the formation of a carbonyl compounds, aromatic carbonyl compounds generated, that is 2-hydroxy estophenone or 4-hydroxy estophenone. This is the general freeze rearrangement reaction. This is called as general freeze rearrangement reaction. This is the ortho product. Actually, this ortho product is generated at lower temperature. This is ortho product, ortho-hydroxy acetophenone. Ortho-hydroxy acetophenone. This is para-hydroxy acetophenone. These two reactions. When you are using higher temperatures or in between the 120 to 160 degrees, both the mixtures are generated at almost, it is 30%, it is 70%. But at one particular 120 degrees centigrade, it leads to the formation of para product is more predominant. At 160 degrees, ortho product is more predominant. That's the temperature dependent reaction. This one is, and the same reaction is carried out at the photochemical condition, not only for the esters, aromatic esters. It can also conduct the same reaction for the ethers and amides. Also use the same examples. Enamines are also aromatic. Imines are also producing, use the freeze rearrangement reaction. Okay, how it is happen? You will observe some examples here. Just you take the same example, that is same phenyl acetate is taken. Phenyl acetate is taken. Now it is irradiated with light in presence of alcohols, butanol or ethanol. You can take it anything. That is also solvent dependent, but here the both are acting as same pathways, same effect on the substrate. Therefore, it leads to the formation of two products are here. One is it is very much similar to the conventional freeze rearrangement, but the highly stereospecific. It is dependent on light, wavelength of the light, whatever the light you are using. Based on that, the products are generated. Now this is the ortho-hydroxy acetophenone, POCH3. Similarly, para-hydroxy acetophenone. These are the two products are generated, but the major product or minor product depends on the wavelength we are using. Now, based on that, we can define that freeze rearrangement is a rearrangement of carbonyl group from the oxygen or nitrogen in a ester or amide from one position to the another position, that leads to the formation of corresponding carbonyl compound in the light, are known as photofreeze rearrangement reactions. Or simply you can define that freeze rearrangement of aryl esters can also be carried out in the presence of ultra UV light. If predominantly the reaction takes place, the rearrangement of carbonyl group or alkyl group or aryl group from oxygen or nitrogen to the ring, then it leads to the formation of various derivatives of aromatic compounds in this reaction. So, other example for the photofreeze rearrangement is you take the ortho-hydroxy phenyl acetate. That means you take the same ortho position. One of the ortho position is blocked with the hydroxy group. One of the Ortho position is blocked with the hydroxy group. Then it is irradiated with red under the same condition. That leads to the formation of two products. One is the para substituted product. That is 3,4-dihydroxy estophenone. 3,4-dihydroxy estophenone. This is one product. And the second product is ortho substituted product, that is CH3 2,3-dihydroxy products. 2,3-dihydroxy products are generated. Similarly, not only esters, ethers are also can participate in the phase rearrangement. Now, actually, what's happening? We are using the solvent, ethanol or butanol or any other solvent. A solvent cavity is generated. A solvent cavity is generated around the substrate. This is the substrate. So, for example, you take this is the substrate. Now, the substrate is undergoing the. Now we are coming to the mechanism. The substrate is undergoing the. This is the CH3. Now it is treated as a carbonyl compound. It is the ester group is considered as a carbonyl compound. Now it is undergoing homolytic cleavage. Therefore, it generates the two radicals in the solvent cavity. This is generating the phenoxy radical and a carbonyl radical is generated. This phenoxy radical abstract the proton from this ortho position or abstract from the ortho position or para position. Now it leads to the formation of phenyl radical. This phenyl radical combined together this carbonyl radical, then it leads to the formation of corresponding products. Okay, similar. Therefore, this is the solvent cavity. Under this, within the solvent cavity, there are two radicals are generated. These two radicals are rearranged to form the new products. Then, such kind of reactions are called as intermolecular rearrangement reaction, not the intramolecular rearrangement reaction. That is not the intermolecular rearrangement reaction. Because suppose if you are using two different esters in the place of methyl group, we are taking the phenyl group here. Two esters are participating in the same reaction. We need to observe the crossover products. Whenever we are considering the conventional phase rearrangement, it is taking place intermolecular rearrangement because crossover products are generated. But in this case, crossover products are less predominantly observed. Therefore, this is the intramolecular rearrangement reaction. Now, the same reaction is carried out for the ethers also. Suppose this is the ether, an aryl ether. This is an irradiation. Then it leads to the formation of alkyl phenols. Ortho-alkyl or para-alkyl phenols are generated. The R group is alkyl group. Then it leads to the formation of ortho or para-alkyl phenols are generated. Similarly, amides can also generate the amides, especially anilates. These are the anilates. Instead of esters, you can take the anilates. You can take an estanilide, or in place of methyl group, that is estanilide. If you take the estanilide, it is irradiated with light. This is the aromatic amide. Then it leads to formation of such kind of products are not generated in conventional phase rearrangement reaction. These products are also not observed in the conventional phase rearrangement reaction, but in the photophase rearrangement reaction produces the specific products. Due to that reason, photofreeze rearrangement is more important to synthesize the products which are not synthesized by the conventional freeze rearrangement. Ethers and amides and imides are not generated, are not participating in the participate in the conventional freeze rearrangement reactions, but the same substrate molecules can react or can undergo the rearrangement reaction in the photochemical conditions. Therefore, that is known as photofreeze rearrangement reactions. These are the specific reactivity shown by the amides and ethers under photochemical conditions. This is the product, and this is the second product. There is a para substituted product. Similarly, if you take allyl ethers, enol ethers or allyl ethers, that means especially freeze rearrangement, it requires aromatic substrates are important for the conventional freeze rearrangement reaction. Or we can also alternatively, aromatic substrate molecule can only undergo photofreeze conventional freeze rearrangement reaction. But in the case of photofreeze rearrangement, aromatic substrate is not mandatory. Aromatic substrate is not mandatory. Suitably substituted unsaturated molecules are sufficient to undergo the photofreeze rearrangement reactions. For example, here enol esters. This is not a aromatic compound, but a cyclic olefin, cyclic enolates, especially cyclic enolates. Enol esters. These are known as enol esters. It is also called enolates. Enol esters, which is on irradiation, then it leads to the formation of cyclohexanone derivative, or we can also call it as 2-oxo cyclohexanyl phenol, simply methyl ethyl benzophenol, like that. We can also label like this. Okay, right? This is the second position of cyclohexanol, 2-oxo cyclohexanyl phenol. This is the IUPAC name. Similarly, other examples. These are all very specific examples we have seen in the photofreeze rearrangement. This the same kind of reactivity is not observed in the conventional freeze rearrangement reactions. Here, yields are also very much higher when we compare to the conventional freeze rearrangement, because the conventional freeze rearrangement is carried out in the thermal condition and also solid phase reaction. In that solid phase reaction, we know that the collisions between the reactants are not successful in all the cases, and radical transfer or radical rearrangement is not also taking place, successful rearrangement. Due to that reason, the yields are very, very low in the case of conventional freeze rearrangement, but this reaction is carried out in the solvent medium in the photofreeze rearrangement conditions. Therefore, it leads to the formation of higher yields of the products. This is the enol esters. This is also one enol esters. This enol ester generates this kind of rearrangement product. This is both the two ortho positions are blocked. Now it leads to the formation of, there is the steric hindrance is created for the para position. Due to that reason, this acyl radical is not shifted to the para position. Only ortho substituted product is generated. Okay, here. Suppose here the two conditions are there, two chances are there, whether it is maybe moving here or here. But here the keto group is there. This keto group somewhat creating the hindrance to this fourth position, that leads to the formation of only ortho migration or ortho rearranged product is generated. This is known as photofreeze rearrangement. We have several examples in our book. You can also see that. And in imines also. Enamines, you see that enamines. What are enamines? You know that a double bond attached amines are known as imines. These are known as imines. Right? Enamines. This is known as enamine. Right? This enamine is done irradiated with light. That leads to the formation of this migration of this group. Just the rearrangement, you can see, you can observe that this R group will be migrated to this position, carbon position. Then it leads to formation of imine is generated. This is the amine. In amine, now the second resulted product is imine. Simply you can call it as CH2, sorry, CH3 or CH2NH2. This is known as amine. Now it is rearranged like this. For example, or it is undergoing the reduction. Then it leads to the formation of NH, CH double bond NH, elimination of some hydrogen. That is known as imines. Is known as imines. Similarly, here the photofreeze rearrangement, the enamine, this is the ene double bond, amine is undergoing photofreeze rearrangement. That leads to the formation of a C double bond N. Just this is the methyl group. This is the methyl group. Now this R group is shifted to this carbon. It becomes a saturated one. That leads to methyl, and R group. This is known as imine. Enamine is generating the imine. This is also known as photofreeze rearrangement reaction. Photofreeze rearrangement reaction. Okay, this is about the photofreeze rearrangement, and I have already explained the difference between the conventional freeze rearrangement and photofreeze rearrangement. Okay, so many variation is there when you conduct the same reaction. Conventional freeze rearrangement, yields are low. All reactants or all substrate molecules will not undergo rearrangement reaction, freeze rearrangement reaction. And also here conventional freeze rearrangement reaction requires a catalyst or reagent, that is the aluminum chloride. This aluminum chloride is highly volatile in nature. Whenever we are heating, it evolves the chlorine gas. Therefore, it is toxic in nature to the atmosphere. And third condition, yields are low. It is a solid phase reaction because we are mixing together. We are not using the solvent in the reaction. Therefore, the rearrangement takes place between the substrate and radical is very in difficult manner. Due to that reason, the product's yields are very low. But when we come into the photofreeze rearrangement, we are using only solvent. There is no other reagent is used in the reaction. That is the environmentally friendly reaction. This one, the first thing. And the second thing is yields are high because the solvent medium reaction, the contact between the substrate and radical is more, because the solvent cavity is generated around the substrate. Whenever we are irradiating, the two radicals are generated within the cavity. Therefore, the rearrangement takes place intramolecularly. Therefore, the products are generated with the high yields. And final difference is all substrate will not participating in the conventional freeze rearrangement because only aromatic esters can participate in the freeze rearrangement reaction in the conventional mode. But when you come into the photochemical conditions, almost all the required substitution is there, or suitably substituted substrate is there that will participate in the photofreeze rearrangement. Therefore, it leads to the formation of diverse range of products in the photofreeze rearrangement reactions. Now, the common feature in all these reactions, they are not affected by the triplet sensitizer. This is the direct irradiation can use the different photofreeze rearrangement products. Therefore, photosensitization or triplet sensitizers are not required. Or it is also not included any triplet quenchers because the triplet state is generated. Suppose in the reaction, the triplet state leads to the formation of photofreeze rearranged products. But the quencher is not required because it is not undergoing a cyclic reaction. After the formation of product, the reaction stops there. Therefore, and also this reaction always we believe that the singlet excited state is participating in the reaction, not the triplet state. N2 5 star singlet state will not affect the sensitizer or will not affect by the pincher in this reaction mechanism, in this reaction pathway, and formation of the product stereochemistry is also not affected by the triplet pincher and sensitizer. Due to that reason, the photophase rearrangement is proceeds through the formation of N2 5 star singlet state transition state only. Therefore, the migration of radical is proceeded or takes places through the formation of N2 5 star singlet state. Now coming to this Norris type 2 reaction or Norris type 2 cleavage. Next reaction is Norris type 2 reaction. Yes. In previous case, Norris type 1, we seen that alpha cleavage. What's happening in the Norris type 1 cleavage? There is a alpha electrons are partially migrated to the carbonyl oxygen of field n orbital. Due to that reason, the bond pair of electrons more towards the oxygen, that is the electronegative oxygen present in the carbonyl group. That is the reason to undergoing the alpha bond in the alpha cleavage, that is homolytic cleavage, leads to the formation of two radicals at alpha position. But here in the Norris type 2 cleavage, this reaction is called as gamma abstraction reaction. First, the substrate requires the gamma hydrogen to undergo the Norris type 2 cleavage. Therefore, the substrate is the minimum requirement is the substrate is what here? The carbonyl carbon or the carbonyl compound. The carbonyl compound is undergoing the Norris type of cleavages. This carbonyl compound at least is having one gamma hydrogen. That gamma hydrogen is undergoing the gamma abstraction by the carbonyl oxygen. Then it leads to the formation of 1,4 biradical intermediate. That 1,4 biradical intermediate may further undergoes the cleavage, beta cleavage, or there may undergoes the cyclization that leads to formation of different products. Therefore, this reaction is occurs in ketones with gamma hydrogen. The products are an olefin or a smaller ketones or a cyclic product. This is known as this is also known as, because after the beta cleavage, a unsaturated product is generated. When unsaturated products are generated, elimination takes place. When elimination is observed in a reaction, then it leads to the formation of unsaturated products. Therefore, this is also known as photo-elimination reactions. Therefore, the initial step is abstraction of gamma hydrogen atom by the photo-excited state of the ketone yields to 1,4 biradical. This 1,4 biradical subsequently cleave to an olefin and enol. That is the photo-elimination. Or this photo 1,4 biradical may undergoes the cyclization that leads to the formation of cyclic product. Here I am going to take one example with with the delta hydrogens. This is the carbonyl compound. Just a minute. Yes. Right. A generalized carbonyl compound with gamma hydrogens. We take this one is alpha, beta. This is the gamma position. This is the known as gamma hydrogen. That hydrogen is gamma hydrogen. Now, whenever we are carried out the Norris type 2 reaction, yes, gamma hydrogen is abstraction takes place. Gamma hydrogen abstraction. When the gamma hydrogen is migrating, a gamma carbon and hydrogen bond is undergoing homolytic cleavage. That is, you can show like this. This is the homolytic cleavage that leads to the formation of hydrogen radical and a gamma carbon radical. Simultaneously, the carbonyl carbon oxygen bond will be undergoing the homolytic cleavage that leads to the formation of 1,4. This hydrogen is abstracted with oxygen that leads to OH, right? Then here the radical is generated. This is the alpha carbon, this is the beta carbon, and this is the gamma carbon, and R prime. It's the R. Now, We count it. 1, 2, 3, 4. Now this is known as 1, 4 biradical intermediate. Biradical intermediate. This biradical intermediate further undergoes or further chooses two pathways. That is the photo elimination one pathway and the cyclization. Photo elimination or cyclization. In the photo elimination, it is undergoing this is the alpha bond, this is the beta bond. This beta bond, carbon-carbon beta bond is undergoing homolytic cleavage. Now, it leads to the formation of two biradical intermediates. That is one OH R, and another one is the beta bond and gamma bond. Both are having beta carbon and gamma carbon. Both are having a radical in nature. Now, these two radicals combine together in the homolytical manner that leads to the formation of olefin, or enol is the product. Enol alcohol is there. This is the enol. Now it is the tautomer of carbonyl compound that leads to the formation of ketone again, but it is the lower carbons containing ketone. Ketone is the one product, and this diradical forms the pi bond between the carbon that leads to the formation of olefin. This is the olefin is the product, right? That means the beta bond cleavage leads to the formation of two products. One is the enol product and another one is the olefin product. And the same 1,4 biradical is undergoing the cyclization. That means the 1,4 position radicals is homolytically combined together. That leads to formation of a cyclobutane product is generated. A cyclobutane product is generated. That is OH R prime. This is the product. Now this is the cyclobutane derivative. This is known as Norris type reaction. And the mechanism. Also, you can consider it as mechanism. Now, here also the reactive intermediate, the substrate participating in the reaction with the N2,5 star singlet state as well as N2,5 star triplet state. Both the transition states are both the electronic excited states are participating in the reaction that leads to the formation of this type 2 Norris type 2 products. Okay. Now, here the gamma abstraction step is whatever the first step it is, formation of 1,4 biradical. How it is generated 1,4 biradical intermediate? That is gamma hydrogen abstraction. This gamma hydrogen abstraction reaction is the reversible reaction. How it is reversible reaction? We can verify that the same reaction after formation of 1,4 biradical from the substrate. This is the carbonyl compound. Hydrogen R radical. This is the alpha bond, beta bond, gamma bond. Alright. Now it is unirradiated. It may generate the first singlet state or first excited state and our triplet energy state will be generated. Right. Now it forms the 1,4 biradical by the gamma hydrogen abstraction. Now the biradical 1,4 biradical intermediate is generated, OH R prime. This is the 1,4 biradical. After formation of 1,4 biradical, we mix it a deuterium containing solvents like deuterated ethanol or deuterated methanol or deuterated water, D2O. Now the reaction leads to the formation of other product, the same substrate molecule, but it contains the deuterium at gamma position. Now the same product is generated, same carbonyl compound is generated, but it contains the deuterium at gamma position. Now the formation of deuterated product, deuterated substrate from the 1,4 biradical indicates that the Norris type 2 reaction, Norris type 2 reaction, first step is reversible. First step is reversible. The formation of deuterated product indicates the Norris type 2. First step is reversible reaction. How it is happened? This reaction is conducted with the ordinary substrate after formation of 1,4 biradical, or in between the reaction we are adding the deuterated solvent like deuterated methanol or deuterated water or deuterated thioalcohols, deuterated N-butyl thioalcohol also used for the monitoring the reversibility of the first step of the Norris type 2 reaction. C4H9 deuterated alcohol that leads to the formation of deuterated product. That is, deuteration is takes place at gamma position. Gamma carbon indicates that this step is reversible. This step is reversible. Therefore, esters, 1 diketones and beta keto ethers with gamma hydrogen undergoes Norris type 2 cleavage, because all these are having gamma hydrogens. All these are having gamma hydrogens. Look at here some other examples. In esters, ethyl esters. Ethyl ester is the example. This is the ethyl ester. If there is no gamma hydrogens, there is no question of there is no reaction of the Norris type 2 cleavage. Now, this is the beta carbon, alpha position of OH of the ester, and beta position. This is the beta carbon. This is the gamma carbon. Now, the cleavage between the gamma carbon and hydrogen homoletically, this hydrogen radical is abstracted by this oxygen that leads to the formation of OH, a radically generated ester carbon and oxygen. This is the beta position. At the beta carbon, it is having 2 methyl carbons, methyl positions. Now, 2 methyl groups are there here. This is 1,4 biradical. Now it is undergoing beta cleavage. It is the beta bond cleavage that leads to the formation of this one, beta bond cleavage. Now it leads to the formation of a carboxylic acid is generated. How it is? Look at it here. A oxygen radical is generated. First, oxygen, a diradical intermediate is generated. OH is there. Now it leads to the formation of an acetic acid is generated. If it is methyl group, it is acetic acid, or a carboxylic acid is generated. Simultaneously, a substituted olefin is generated. That means 1,2-dimethyl, 3,4-dimethyl, tetramethyl, ethane diradically generated. Both will be combined together. Then it leads to formation of tetramethyl ethane, or 1,2-dimethyl 2-butane is generated. These are the products. Okay, several examples are given in our book. Please read once, you can understand the mechanism of the reaction. In the carbonyl compound, gamma hydrogen is there. It may take place or Norris type 1 reaction and Norris type 2 reaction. Both are compete to each other. For example, here I am going to take 2-pentane. 2-pentane is CH3, C double bond, 2-pentanone. Sorry, 2-pentanone. This is the 2-pentanone. 2-pentanone, which is on irradiation. We can get the Norris type 1 products and Norris type 2 products. That is depends on the type 2 reaction always predominates in vapor condition. In solvent condition and solvent condition, type 2 reaction will be predominant. This is the important thing you need to remember, that Norris type 2 cleavage is produces the products under solution phase reaction. In the vapor state reaction, that means higher temperature in the vapor condition, Norris type 1 cleavage will be predominant. Therefore, if you it takes the two paths. One is the vapor condition, vapor phase condition. Then it leads to the formation of Norris type 1 product, that is alpha cleavage maybe takes place. Alpha cleavage is taking place, that means more stable more stable radical is generated. Then it leads to the formation of diacetone is the product, CH3, C double bond O, C double bond O, CH3, along with some acetone, CH3, CO, CH3, and some simple alkane. That means simple alkane means 3 carbons are there. This chain is broken from this carbonyl compound. Therefore, simple N-hexane is generated. N-hexane, NC6H14 is generated. These are all Norris type 1 products. These are all Norris type 1 products. Now coming to the Norris type 2 product. This is the carbonyl carbon, alpha position, beta position, gamma position. The hydrogen is abstracted from this position. That leads to the formation of Norris type 2 products, that is acetone. How the acetone is generated, how the olefin is generated, how the cyclobutane derivative is generated, already explained in the mechanism. You can review again. Once you see the mechanism, you can understand how these products are generated. Okay. Here you need to, in the Norris type 2 cleavage, you need to understand that, you need to remember that both are compete to each other when the gamma hydrogen is available in the carbonyl compound. Norris type 2 cleavage also takes place, Norris 1 is also takes place. But here the trick is, if the reaction condition is vapor phase condition, that means you are boiling at pyrolytic conditions, if the substrate is converting into vapor phase, vapor condition or gas state. In the gas state, it is undergoing the alpha cleavage that leads to the formation of Norris type 1 products. If you are conducting the reaction, at solution phase and irradiating light at the solution phase, that means you are not converting the solution medium to the vapor condition. Therefore, it leads to the formation of Norris type 2 products. Therefore, in the condition, Norris type 2 products are generated with the various ratios. Okay, this is about the Norris type 2 cleavage. Okay, here we are discussed here Norris type 1 cleavage, Norris type 2 cleavage, and photofreeze reaction. These three reactions are very much important for the examination. You need to prepare them. Okay, now coming to the photochemical reactions of alpha beta unsaturated carbonyl. Till now we are studied about the photochemical reactions of simple carbonyl compound, that may be aliphatic carbonyl compounds or aromatic carbonyl compounds. They are undergoing photoreduction reactions, Paterno-Bichy reactions, Norris type 1 cleavage, Norris type 2 cleavage, photofreeze rearrangement. These 5 reactions are shown by an aliphatic or aromatic carbonyl compounds. When you consider because in these conditions, that means all these 5 reaction conditions, carbonyl compounds are excited to the first excited state, that is N2 star 1, first excited state, S1 state, or N2 star triplet state, T1 state. These 3 excited states are participating or generating in the reaction that leads to the formation of various products and various pathways and various reactions. Therefore, these 5 reactions, what is that? Photoreduction, Paterno-Bichy, Norris type 1, Norris type 2, and freeze rearrangement. These 5 reactions are observed in the allylic carbonyl compounds or aromatic carbonyl compounds. But the same reactions are not observed when we are taking the alpha beta unsaturated carbonyl compounds. What are the alpha beta unsaturated carbonyl? The carbonyl carbon or carbonyl double bond is having the double bond at the alpha position. That alpha position means the alpha carbon and beta carbon are associated with the olefinic bond. That carbon compounds are known as alpha beta unsaturated carbonyl compounds. These alpha beta unsaturated carbonyl compounds are not easily generate the N2 5 star triplet state. These are associated with the 5 to 5 star triplet state because once these alpha beta unsaturated carbonyl compounds are irradiated with light, first they are generating the N2 5 star singlet state energy. This singlet state energy transfer the energy with the intersystem crossing the nearest energy level. In this case, the nearest energy level is triplet state. First T1 state is 5 to 5 star energy level, not the N2 5 star triplet state energy. Due to that reason, N2 5 star singlet state energy is undergoes the intersystem crossing. Therefore, the energy transfer to the T1 state, that is 5 to 5 star. Therefore, the reaction pathways are changed when we compare to the allylic carbonyl compounds and aromatic carbonyl compounds. Therefore, these alpha beta unsaturated carbonyl compounds are undergoing cyclodimerization, cycloadditions, cis-trans isomerizations, reactions. These three kinds of deconjugation reactions. The four kinds of different reactions are participated. These are different from the simple carbonyl compounds, that is allylic carbonyl compounds and aromatic carbonyl compounds. Now, first coming to the cyclodimerization reactions. The cyclodimerization reaction, these are involving first coming to the photochemistry. Take the heading photochemistry of. I think my drawing is very thin, not appear anymore. Right, I'm increasing the thickness. Yes. Photochemical reactions of alpha comma beta unsaturated carbonyl compound. First one, we take cycloaddition reactions. Cycloaddition reactions. We have already same cycloaddition reactions are discussed in the pericyclic reactions. What is the pericyclic? We have pericyclic reaction, three kinds of reactions. So many of you are absent during the pericyclic reaction discussion. Pericyclic reactions are three types. One is the electrocyclic reaction, second one is cycloaddition reaction, third one is the sigmatropic reaction. The second type is cycloaddition reaction. What is the cycloaddition? The conjugate addition of 2,5 systems produces the cyclic compound or cyclic adduct. Or reverse is the cyclic adduct is broken down to the two 5 systems, that is known as cycloreversion. The forward reaction is cycloaddition, the backward reaction is cycloreversion. Similarly, here the alpha beta unsaturated carbonyl compounds are also participating in the cycloaddition, where the pi bond between the alpha and beta carbon is behaving like a olefin. Therefore, they are undergoing the cycloaddition. Here I am going to take one example: cyclo alpha beta unsaturated cyclopentanone. This cyclopentanone to pentane cyclopent2enone. This is the starting material. Whenever you are irradiating with light, it may produces two kinds of products. Therefore, these 5 bonds two equivalents of molecules are participating in the reaction. Cyclic adducts are generated. Okay. This product is known as head-to-head dimerization. Head-to-head dimerization. And the second product is head-to-tail dimerization. Just for the reference, what is the head-to-head, head-to-tail? Now, both the carbonyl groups are on the same side. This is known as head-to-head dimerization. Head and heads of the two. This is known as tail end. This is the tail end. Both the heads and both the tails are same side. That is known as head-to-head or tail-to-tail dimerization. Now it is known as head-to-tail dimerization. This is head-to-tail, head-to-tail. Now this product is known as head-to-tail dimerization product. Now, we can prepare several kinds of cyclohexanone derivatives or cyclobutanone derivatives, cyclobutane derivatives by using these cyclodimerization reactions. Okay. This reaction is sensitized by the xanthones or the triplet sensitizers, are quenched by the piperylene like triplet quenchers. Triplet quencher. Now this reaction involves N2,5 triplet state that leads to the formation of head-to-tail dimer is the major product. In the polar reactions, we take the polar reaction. Always this reaction is involving N2,5 triplet state energy. Sorry, not the N2,5, 5-5. 5-5 triplet state energy. This 5-5 triplet state energy generation, after generation, we are using suppose two kinds of solvents. One is the polar solvents, another one is non-polar solvents. In the polar solvent, it leads to the formation of head-to-head product is the major product. In the non-polar solvents, it is the head-to-tail product is minor product. That is, the solvent condition influences the formation of the dimer product. The solvent which is used in the reaction that influences the product formed in the reaction, right? Similarly, the reaction takes place with the cyclohexaenone or malic anhydride or 1,4-naphthaquinone or coumarin leads to the formation of dimer products. This reaction, all these reactions are sensitized by the benzophenone, acetophenone, thioxanthone or naphthalene, and also quenched by these reactions are also quenched by the piperylene like molecules. In all the cases, identical regions are obtained on in the direct radiation, and the reaction is sensitized by the triplet state. That means the products which are generated in the reaction, whether it is maybe direct irradiation, when we are using the direct irradiation, the substrate molecule which can directly produce the triplet state energy, or we are using the triplet sensitizer, that is also leads to the formation of N2,5 triplet state energy. Both the cases, direct irradiation is also produces the 5-5 transition state, triplet transition state. When you are using a triplet sensitizer, there also it can generate the 5-5 transition state, triplet state transition state. In both the cases, the products are generated in the reactions are same. There is no change. That means similar reaction condition in both the cases, direct irradiation or triplet triplet state energy sensitizer. In presence of triplet state or photosensitizer, simply you can call it. We have several examples. I will discuss 2 or 3 examples here. If you are using alpha beta unsaturated cyclohexanone derivative, this is cyclohexa 2-enone. Cyclohexa 2-enone, which is on direct radiation. It is also leads to formation of head-to-head product or head-to-tail product. That is depends on the solvent condition. That is, if you are using the polar condition, polar solvent conditions, that leads to formation of head-to-head product. Or we are using the non-polar condition, that leads to formation of head-to-tail product. Right. This is the head. This is the head of the second substrate. Now this is known as head. Oh, sorry. Head to tail is already given. Head to tail is already given. This is the product is head to head product. This is the head to head product. This is the head to tail product. Both products are given. When you're using the malic anhydride, this is the malic anhydride. Malic anhydride, which is on irradiation. This is also leads to the formation of only single product is generated because the 2 ketones are there, symmetrical ketones, carbonyls. This is the product. You cannot say what is the head-to-head, head-to-tail here. Only one product is generated. It is the highly specific. You can say that. Next, 1,4-naphthahydroquinone. That is also here. The most important is Tumerians. It is the oxygen heterocyclic. This is the coumarin. The 2 molecules of coumarin are irradiated with the light. Then it leads to formation of oxygen. Only head-to-head product is generated here. Yes. All the head-to-head product. That is the double bond is here. That is participating in the saturation. Cyclodimerization. Sorry, dimerization. Now coming to the cycloaddition reactions. This one is cycloaddition. This is the cyclodimerization. Cycloaddition can use the 4 plus 2 cycloadditions or 2 plus 2 cycloadditions similar to the pericyclic reactions. Cycloaddition reactions. Simple, can take it alpha beta unsaturated cyclohexanone. This cyclohexa 2-enone. which is reacted with different kinds of substrates, 5 substrates, CH3, CH3, a cyclo. This olefin is act as a 2,5 system. This double bond of the alpha beta unsaturated ketone is acting as a 2,5. Therefore, this reaction is 2 plus 2 cycle addition. Now it leads to the formation of a cyclobutane derivative. Cyclobutane CH3 CH. Okay. If you use several kinds of substrates, you can get the different kinds of products. You can just see this. See the book at the respective unit. You can get the several examples. And not only olefins, alkanes are also participating in the cycle addition. Cyclopentanone derivative, that is cyclopenta-2-enone, is reacting with alkyne, that is 2-butyl. Is an radicalite that leads to formation of cyclobutynyl derivative. This is the product. Now coming to the cis-trans isomerization reaction. Cis-trans isomerization, generally when the enone systems is part of the larger ring, this kind of cis-trans isomerization reactions are observed. They are not undergoing the cycloadditions or the cyclodimerization due to the ring size. Whenever we are taking the ring size of the alpha beta unsaturated carbonyl compounds, cyclic carbonyl compounds, they are not undergoing the cycloadditions or cyclodimerization. That is the reason those cyclic systems are not arranged in the planar ring form. Planar ring form, and five electrons are they are facing some steric factors. They are not undergoing cycloadditions or cyclodimerization reaction. Due to that reason, they are undergoing cis-trans isomerization reactions. That is cis-trans isomerization of cis-trans isomerization of alpha beta unsaturated carbonyl compounds. Unsaturated carbonyl compounds. For example, cyclo-octa-2-enone. Cyclo-octa-2-enone. Now, first you take the this is a cis-octa cyclohepta-2-enone. Look at here, 2 hydrogens are there. Therefore, this is two hydrogens are on the same side. Therefore, this double bond. This double bond. This is cis isomer. Whenever it is an irradiation, it is complete. It is almost, we look into that, it is a planar form. Now, whenever we are irradiated, it is the planar form rapidly converting into non-planar form. During the arrangement, the steric strains repulsions will be decreases. The arrangement takes place in such a way that to reduce the steric strains and increasing the stability energy. Okay. Now, these are the products. Look at here. These two hydrogens are trans to each other. These two hydrogens are trans to each other. Now this is a cis cyclohepta-2-enone. This is trans cyclohepta 2-enone. Actually, this is very much unstable. At the lower temperatures, you can find it by using spectral methods. Right? Similarly, cyclooctane, cyclooctane 2-enone is also produces the same product, same cis-trans isomerization reaction. This is a planar product, planar ring system. Cis cyclooctane 2-enone, which is on irradiated with light. Now it is the cis form. Two hydrogens are on the same side, similar comparable bonds are on the same side, carbon-carbon. Now it is an irradiation that leads to the formation of hydrogen. These two hydrogens are trans to each other. This is the trans product. Now the trans cyclooctane 2-enone. Now this is isolated. Now this is the product. Right. Deconjugation. Deconjugation means we have seen alpha beta unsaturated. Next kind of reactivity is deconjugation. Deconjugation should take alpha beta unsaturated ester. This alpha beta unsaturated ester this is the alpha position, this beta position. At a gamma position, hydrogens are there. Suppose gamma position hydrogens are there. Now first it is which is on irradiated light. It produces the corresponding 5 to 5 star transition state. 5 to 5 star transition state. Later it is excited. This is the excited transition state undergoing the cis-trans isomerization. After cis-trans isomerization, we can take hydrogen, C double bond O, OET. Now these hydrogens are nearer to the ester group. One of the hydrogen is nearer to the ester. Now this gamma abstraction takes place similar to the Norris type 2 cleavage. This gamma hydrogen abstraction is there. That is bond. This arrangement takes place. Now the product is hydrogen, OH and OED. Now again 1,3 hydrogen shift takes place. 1,3 hydrogen shift takes place. That is this is the 1 position, 2 and 3. This hydrogen shifted to this position. Now this leads to right. Then the product is beta gamma unsaturated OET CH2. Here I do this. This is we coming to the alpha, beta, gamma. This is beta gamma unsaturated ester. Unsaturated ester. It means called deconjugation. Here the 5 bonds are in the conjugation. After the reaction, this conjugation will be disappear. Due to that reason, this reaction is called deconjugation. Now coming to the Photochordism. This is the last concept in this unit. Photochordism. Photochordism. Some of the molecules, whenever we are irradiated, they are undergoing the beta hydrogen abstraction that leads to the formation of some color generation. Whenever we are withdraws the radiation, then they are revert back to the original substrate. This is known as photochordism. A colorless or some colored compounds. For example, here orthomethyl benzophenone, orthomethyl benzophenone, which is a colorless substance. Whenever we are irradiated, that will be a gamma hydrogen is shifting to this oxygen of carbon. Then that leads to the formation of this kind of product. CH2. This is photoenol. And orthomethyl benzophenone. Whenever we are withdraws this light, it will be revert back. That color will be disappear. Murali, ఒక్క 2 నిమిషాలు క్లాస్ అయిపోతుంది. Then this kind of photochordism is used in optical lenses. Suppose we have seen very generally seen optical glasses. When we are entering into sunlight, that will be converting into black. Again we are coming to the shade, then they restore to the a transparent glasses. That means that is called as photochordism. Optical glasses we are wearing, when we are walking in the sunlight, they are slowly converting into black shades. That is, it gives the cooling to the eyes. That means it prohibiting the transmittance of the bright light through them. Once we are entering into the shade, that they are converting into a white glasses. That is called as photochordism. That is due to the reason is somewhat this kind of chemicals are coated on the chemical that optical glasses. They are acting as a optical photochordism. Whenever we are irradiated with the light, they are converting into color substance. The color substances abstract the or prohibit the bright lights. Then when suppose that sunlight is disappearing or irradiation is stopped, then they are converting into original substrate. This is known as photochordism. Okay, this unit 12 is completed. In the next class I am going to I will start the unit 13. Okay, now I am stopping this session. Thank you. If you have any doubts, you can discuss in the next session. Thank you very much. Murlis are waiting for you. You can join the my login, whatever the login given to it. Paper 5 login is there. You log into that. Right? Thank you.